Hi everyone, Mr. Coxford here. In today's video, we're going to be looking at electric current as well as power and how that applies to electric circuits. So let's get started. The first thing we need to define is what is an electric circuit. So an electric circuit is a closed loop through which charges can continuously move. It needs to be closed, right? It can't have any breaks in it. It has to be a closed loop, and the charges are going to be moving continuously, just looping through that entire circuit. And so then we define current. Current is the flow of charges within that circuit. So if we have a closed circuit, we will have current flowing. So now, what do we require in a circuit? Well, here's an example of a circuit that is has a closed loop that has current flowing through it. If we have a light bulb that's lit, we know that that circuit has a light bulb. There's some wires connecting it to a battery pack, and the fact that the bulb is glowing, that tells us that charges are flowing. So to establish an electric current, we have to have a closed conducting loop from the positive terminal of a battery to the negative terminal of a battery. Let me show you a quick example of that. So here we have a very simple circuit. We have a battery, we have a light bulb, and we have some wires, and then I have a switch here. And we can see that when the switch is open, we do not have a closed loop. We have an open loop, right? Because there's a break here. The positive terminal of the battery is not connected to the negative terminal of the battery. Whereas if we close this switch, we can see that while it's not direct, it travels through the light bulb, the positive terminal of the battery is connected to the negative terminal, and we have some charges flowing, and the light bulb is lit. Perfect. Now, the other requirement is there has to be an electric potential difference across the two ends of the circuit. This means that if I take this battery out here, let's just take this out, and let's just connect our wires together. We have a closed loop, but there is no potential difference. There is nothing supplying any energy to our circuit that would allow charges to flow. And so having something like a battery, sticking that back into the circuit, I'm sorry, it's a little messed up, but it still works. Having that battery in the circuit allows that potential difference is giving charges energy. We remember that from our last section. A potential difference means that charges at one end of the battery have a higher energy than at the other end. That means that these charges can flow through the circuit. They are able to use that energy to, in this case, light this light bulb. So those are the two requirements: a closed conducting loop and a potential difference. All right, so let's talk about how we can define current in terms of some values. So current, it's the flow of charges, and it's defined as the rate at which charges flow past a point in a circuit. So if we look at that in terms of an equation, current, for some reason, it's defined as I. I is current. I'm not sure why, but the current I is the symbol for current, is equal to the charge. Remember, Q is charge. I think maybe in the last section we used little q when I was talking about charge. Big Q, charge, which has units of coulombs. Right? Remember the units for charge of coulombs, and per unit time, and time is in seconds. And coulombs per second gives us units of amps, amperes. Okay, so the units for current are amps or amperes, and 1 ampere is equal to 1 coulomb of charge passing through a certain point in a circuit in 1 second. So let's look at some examples of that. Here I have a little section of wire, a little 2 millimeter section of wire. It doesn't actually matter how long that section of wire is, simply that we have a certain amount of charge. It says that 20 coulombs of charge passes through this section of wire in 40 seconds. 20 coulombs of charge is a ton of charge. 40 seconds is actually a considerable amount of time for charges to be flowing. So let's see how much current we have. So if current, the symbol for current being I, is equal to the charge flowing through a certain section in a certain amount of time, if we have 20 coulombs passing through this section in 40 seconds, doing that math, 20 divided by 40, 0.5, and our units for current is amps. We have 0.5 amps of current. Okay, and then our next example says how much charge passes through a 1 millimeter cross section of wire in 0.5 seconds if the current is 4 amps. So again, how long that section is doesn't really matter, but we are going to try and figure out how much charge passes through if we know the current and we know how much time. So rearranging our equation, charge is equal to current times time. We get 4 amps in 0.5 seconds. Tells us that 2 coulombs of charge are going to pass through in half a second if we have 4 amps of current. Okay. Now, when we're talking about current, there is this idea of conventional current. Conventional current, this is used worldwide by scientists. I think this was decided before even scientists knew exactly what was going on a atomic level. They said, we're going to hook up this battery, we're going to call this side of the battery the positive terminal, and we're going to say that current, this flow of charges, is coming out of the positive terminal and into the negative terminal. That is called conventional current. Conventional current. It's the direction in which a positive charge would move in a circuit, out of the positive end of a battery into the negative. Now, in reality, once science developed and we could start looking on a more microscopic atomic level, scientists realized, oh, actually charges flow in the opposite direction. It's not positive charges that flow, it's negative charges. It's electrons that flow. Let me show you. So here, back in our circuit that I messed up, let me just clean this up a little bit. Oh gosh, okay, let me attach that back here just so it looks a little nicer. Looking at this circuit here, what I am showing you here, this side of the battery, the little yellow side of the battery here, there's the positive terminal. This is showing us conventional current, the current that the direction that positive charges would be flowing. Now I'll move my video here. We can see here that in this simulation, we can also show electron flow. If I click on that, you can see that negative charges flow in the opposite direction. They flow at the negative terminal of the battery. Now, it's the same rate, it's the same result. The only difference is the direction of flow. So we have conventional current and we have electron current. The current that we are going to be talking about in this course, anytime I say current, what is the direction of current? I'm always going to be asking about conventional current. Conventional current, it's the convention. It's what scientists have agreed to use, even though we know we're wrong about what's actually flowing. It's just what has been used and what will continue to be used until somebody can convince scientists as a whole to change their minds about that. That's what we're going to use. So conventional current versus, we call this electron current. All right. So we're going to say we're going to use this always. But it's good to understand that electrons are the things that are actually flowing when we're talking about it. Okay, now let's talk about power. What does power have to do with circuits? Well, we know already from previous sections that power is talking about energy and time, the rate at which energy is being used or work is being done. There's a bunch of ways to be talking about that. So in terms of a circuit, well, we know that circuits are designed, the whole point of a circuit is to take that electrical energy, that electrical potential energy, and turn it into other forms of energy, whether we're going to light a light bulb, whether we're going to make some sound, whether we're going to run a motor, whether you're going to run your computer to do a bunch of different things. We're going to be using that electrical energy to convert it into different forms. And the rate at which that energy is converted is called power. And so whether we're talking about a battery supplying that energy, the rate at which it supplies energy, or we're talking about the rate at which a load, some sort of element in our circuit is using that energy. We're going to be talking about those rates. And so we can see here power is either the work done on charge, I missed my E there, over time, or it's the energy consumed by a load over time. The same units that we've had before. A watt is the unit for power. It's simply a joule per second. And you might sometimes see on a device, like a light bulb, for instance, a 60-watt light bulb. A 60-watt light bulb is telling us how much energy per second that light bulb is using. 60 joules per second. 120-watt light bulb would be using 120 watts, 120 joules per second. Now, how is this useful for us in terms of circuits? Because, as I said in the previous videos, we're not actually interested in knowing exactly how much energy a charge has or how much work is being done. We're talking about voltage and we're talking about current. So let's see if we can somehow relate some equations. And so we have a few equations here. Let's start here. We have that current is the rate at which charges flow, charge per second, or coulombs per second, charge over time. We also had in our last section that the potential difference, the electric potential difference, the difference between the top terminal and the bottom terminal of a battery, for instance, is the change in the electric potential energy per charge. Okay, let's take these guys and let's multiply them together. We're going to go the potential difference multiplied by the current, which potential difference, change in electric potential energy over per charge, times current, which is charge per charge over time. And we can see here charge and charge. There's charge on top, there's charge on the bottom. Those cancel out, and we're left with the change in electric potential energy over time. That might look familiar. It's the change in energy over time, which is equal to power. So what that means is we can say that power is this guy. Delta V, the potential difference, times the current. In more simple terms, sometimes we'll just drop the little delta symbol. We'll say that power is equal to IV. This is what you'll see on your equation sheet. The power that is both supplied by a battery. So if we want to know how much power is supplied by a battery, what's the potential difference of that battery? 1.5 volts, 9 volts, whatever it is. And what's the current? How much charge is flowing out of that battery? How many amps of current are flowing out of that battery? Multiply those two together, you figure out how much power is supplied by a battery. We can also figure out how much power is consumed by a circuit element. What's the potential drop or the voltage drop across a certain element? Is it losing 1.5 volts as we go across? Okay, and then how much current is flowing through it? Multiply those together. We can figure out how much power is being consumed, the rate at which energy is being consumed by that circuit element. And the thing about a circuit, conservation of energy says, all of the energy that's supplied is going to be consumed by the time we're done that circuit. And so in a similar vein, the power supplied by the battery, for instance, is going to equal to the power consumed by the circuit elements. All right, so that's an important thing to understand. It's a good check when we get into our circuit analysis to see how much power is supplied, how much power is consumed. Do those match up? If so, we're on the right track. Okay, that's it for today. You have some practice questions here that you can work through, and I will see you in the next video.